So, now we will see how the attack can happen. Let us say there is a parent process which actually forks a child process. Now, this is the page table for the entire system. So, these are all process pages and these are all OS pages. Now, what will this child process do? This child process will access some part of this OS page. Okay. Let us say it is accessing 1 byte of this OS page. So, I can say that move into the register EBX, let us say some let us say this is kth location, I say k. Or I can even say, instead of doing this, I want only 1 byte, I can say move BL, BL is in Intel, it is a 8-bit register, and then say byte of k. Right. So, from this kth location it will come. Obviously, this is going to give us an exception, but that exception will be detected only after this BL basically gets a value, right. So, what will the subsequent instruction it will do? It will just so now after this exception has come, right. So, this one, so after this exception has come for this, after the exception has come, there are going to be some instructions 1, 2, 3 that are following. All that these instructions have done will get annulled, right. So, but let us say there are some instructions here, these set of instructions will leak the value of this BL to the parent process. Right. So, what will happen is, and when it will leak, between the time where there is an exception and between the time where there is an exception and between the time where the value is stored into BL and then an exception is going to rise. So, say let us at time t1 BL gets the value, at time t1 plus delta, this is where exception is raised. The moment exception is raised, whatever I1, I2, I3 is done is gone. So, between this time interval t1, this delta time interval, these set of instructions whatever is following this should somehow leak the value of BL to the parent process, right. Now, what will happen is, once an exception comes here, essentially the child will be terminated. So, once this exception is raised, child will be terminated. At that point the parent process will get the control, right, and it will, the parent process will not do anything about this termination, okay, let it go, but it has got the value of BL. So, then what this parent process will keep on forking multiple child process, and in each time it can get 1 byte or whatever byte, and it will get leak information, and then essentially the entire kernel dump can be got out. So, this is the basic methodology that is followed in Meltdown. The reason again is that there is out of order execution. If it was in order execution one after another, this instruction would have come, this once this instruction finishes, then only if I say I1 can execute. I do not see those if you had seen if you remember in the previous session we have seen one blue bus, right, which is feeding into all the execution unit. If there was no out of order execution at all, then obviously I1, I2, I3 will never execute before this move finishes. But we want optimum, we want performance, and so what we have done, we have allowed out of order execution, and that is a microarchitectural decision that we have taken. And because of that, what happens, before I even realize that this is an unauthorized access, there are other instructions which will basically execute, assuming this is a correct operation. This is also called speculative execution. Sometimes I speculate that this move will work correctly, and I go and execute the other instruction. Because of that, what happens, some data, these instructions will have access to that BL, which is the confidential data, and then now there is the intelligence come here, how I leak that BL to the parent process, because once the exception is raised, all the things that we have done, that I have read BL, but that as a I1 or I2 or I3 I know the value of BL, but the moment that exception happens at this instruction, all these gets automatically handled by the hardware. So in that small time window I need to leak the value of BL to this, right. So now the problem is that the operating system believed that nobody can touch the OS memory at all, right. Now because of the optimization at the microarchitecture level, it did not know about the optimization at the microarchitecture level. Because of the optimization that we have done at the microarchitecture level, what has happened? There is a small window of time where this data could be leaked to another instruction, it is not just it has gone out. Now, so till now, so that is the break. Now okay, some other instructions got it, so what, because once the exception is raised everything will be erased, but then those instructions can do something intelligent to basically send back the value to the parent process, and that is where the challenge, the third challenge comes. Okay. So we had an operating system assumption that got violated because of a microarchitecture level optimization. Now that microarchitecture even thought, right, okay, it is fine if an exception, when they were actually framing this out of order execution, do you think they would not have thought about it? Yes, they would have thought about it completely, saying that okay, anyway let it know, let it get the value of EBL here, BL here, let the other instructions, anyway when the exception is raised everything is going to handle, so what is the issue? These instructions actually exploit a circuit level phenomena, namely it is a cache organization which is a circuit level phenomena to basically leak the information. So there is a side channel, it is called basically a side channel, we will see how it is going to happen. So that is why we have been telling that there is an operating system concept involved that got broken, there is a microarchitectural level concept involved that got broken, and then finally there is a circuit level concept which also enabled this whole attack. So this is 3 layers in the operating system, the microarchitecture and the circuit level jointly trying to get this meltdown in place. So this is our attack. Now what needs to be explained now is what are these 3, how these 2 or 3 or whatever, how are these instructions, we call them, the literature currently calls them as transient instructions, how are these 3 instructions going to leak the value to the parent process. Now this is basically a parent child orchestration that needs to happen. Now what will the parent do? Now let us understand, now we have cache, now I am trying to access memory, if it is a cache hit I say I get it in 1 unit of time, if it is a cache miss then I take x units of time, several say probably if depending upon the cache memory organization it can be 100 units of time, so if there is a cache miss. So and there are performance counters available in all these architecture which will measure the memory access time, which will say whether there is a cache hit or not. Okay. So that is very important, right. So what we can do, what the child process can do is, suppose BL, suppose I have given say so this BL is 8 bits, so 8 is 2 power 8 is 256, correct. I could have 256 cache lines, right, 256 blocks. So let us say every cache is some bytes, say some 32 bytes or 64 bytes. Let us say every cache line is 64 bytes. So 64 is 8. So let me say that 256 into 8 is 1024, right. No, 2048, right. So, so let us go to the next, I will just explain how the cache is now organized, and that will give us a lot more insight into, right. Now, the cache has say 256 lines. So, let me say line 0, line 1, line 2 till line 255. Suppose in my BL I have read say 8, right. I go and so let me say that so I now go and access the line and the address 8 into 64, each is 64 bytes cache line. So, I go and access 8 into 64. The moment I access 8 into 64, just I access 8 into 64, then that line L8 will now be populated, right. So, as a child process, suppose I am reading from some kernel, I get the value 8, immediately I will go and just access, so go read or write something into 8 into 64, right, into an address which is 8 into 64. Then automatically that particular cache line gets populated, right. Similarly, suppose I got, instead of 8 I got 25, I will go and read 25 into 64. So, the L25 will basically get populated. So, what I can do is, as a parent process, I can execute a simple code which will flush all the cache lines. It is very easy to do that. I can flush all the cache lines. So, when the child starts executing, all the cache lines are empty. Now, the child process basically reads say 8. So, it goes and populates only the 8th line, and then what happens, then the exception got raised, everything is annulled, but please note that the fact that there was something updated in the cache cannot be annulled, right. There is something updated in the cache cannot be annulled. So, what will happen is that when I go back to the main process, the main process will do several things. The main process will start accessing L0 to L255, one by one it will access, and there it will go and find out if there is some data entered, there is a hit or not, right. So, L0 to L, suppose L8 was there, L0 to L7 and L9 to L255, it will always be invalid, but L8 it will find something, some access there, right. So, now it will know, okay, the value that was read by the child process is 8. So, this is how the basic information is leaked. So, let us go back to the previous now. So, this is the parent process. What does the parent process do? It will flush the pipe, flush the cache completely, and it will fork a child. What will the child do? It will go and access something in the kernel space, and subsequently there will be an instruction which will, so if it has accessed say some 8, it will go and write into the 8th cache line, and then now some exception will come, the registers everything will be erased, but one thing, what has happened to the cache will remain exact, right. So, now the parent process, when there is an exception, the child actually gets killed, the parent will not do anything, okay fine, it will immediately start accessing all the lines from 0 to 255. It has flushed everything, so nothing will be there except at the 8th. So, there it will take the value, again it will force process, now it will read that BL, now it will write there. So, byte by byte I can recover, and essentially the entire kernel dump I can get. So, I can read from K starting from this point, I am marking it in green here, starting from this point to this point, byte I can read. Every time I will fork a child, I will get the value, fork a child, get a value, fork a child, and I can complete the entire story. So this is how the meltdown attack has taken place. So I will just summarize this whole thing with this particular. What happens is the parent process, as I told you, will spawn a child which launches the attack. The child launches the attack. So what will the child do? It will access the OS region and it will leak the data to EBX. Then it will encounter an exception. Then what will do? The parent process will take over. The parent can kill the child on an exception and it will continue executing. Now the question was that how to transfer the leaked data from the child process to the parent process. So one very interesting thing is the child process cannot write a 1-bit secret data into register EBX to P1 to the parent process, since exception will clear it. Whatever you do, so when the exception comes, whatever the 3 transient instructions did, that will be cleared. So the child process cannot pass the information to the parent process basically using a register, because whatever this child process does after that exception, any instruction the child process executes after that exception, instruction causing the exception, that will be annulled. So what can P1 and P2 do? P1 parent and P1 child, what it can do? They will agree that if the secret, so suppose I am reading bit by bit, if the secret is 1, then P1 must write to location 1000, else if it is 0, it should write some value to location 2000. Effectively P1 parent and the P1 child have shared the secrets through this covered channel. But what will happen is, so this is 1 bit by bit is difficult. Let us say byte by byte, how will I do? P1 writes to page 0, which is 4 KB size, if the data is in EBX is 0. P1 child writes to say page 84 if the data in EBX is 84. Like that I could have 256 pages, I can write to one of these pages. So the P1 child can leak 8 bits of data at a time to its parent process P1P. Now all these writes also will get annulled, all such writes from P1C to P1P will get discarded, because once that exception comes, the hardware will discard all these writes. So again I can't go back. So the next challenge essentially comes, this is the idea of the cache. So what will the parent process do? It will first flush everything and give a fresh cache to this fellow. Now what will the fellow do when it sees a particular value? It will go and access that particular cache. It will not do anything, just access that cache. Now after that the exception will come, then the parent process again starts, and what will the parent process do? So when I do this is called a flush and reload attack. Now the parent process first ensures that the cache does not have any stale data at all. Now the victim actually writes to a cache line in the cache while executing. Now the attacker accesses all the cache lines again, and only one cache line will result in a cache hit. All the other things would be thing, and so we will go ahead. So this is something very interesting, and that is where I will not actually write the data, but I will just get a cache hit there. So then I know that okay, this is the exact value, because the line number where the hit has happened is essentially equal to the value I have written. So by this I can get the value, and so I repeatedly keep spawning child processes and basically get out the dump. So to conclude, I think one of the basic theory that we have been promoting at IIT Madras on these, we say that security is not an isolated phenomena, it spawns across all layers, as we have been talking of in our first slide of my first IS1 course. The entire security spawns across these 5 layers as you see on the screen now, and any security vulnerability is not restricted to one layer, but it is an act of several layers getting together and trying to get out that vulnerability. All the vulnerabilities that we have seen in the past also has some level of misunderstanding between the application and the operating system, right, and some amount of hardware support which was not used. But this is the first attack which has come up and hopefully we don't have such similar attacks in the future, which has exploited certain microarchitecture and circuit level concept. Of course, at the circuit level there is lot of literature, there is a lot of work that is happening on the side channel attacks, basically to leak information. But this attack is a different class of its own, where it actually used the cache, it actually used out of order, and then it also used the fact that the operating system need to have a single page table which has both the OS pages and the process pages. And so that is how this 3 layers have got together to melt down the security feature. So this is a very, very important eye opener, especially for hardware architects, operating system developers, specifically virtualization developers, people who rely on virtualization, basically the VMs. Those are the people who need to worry about this leaking of secret from one virtual machine to another virtual machine. Each virtual machine per se is a process, and even on network routers where we configure say VPNs, multiple VPNs are there, and one VPN should not talk to another VPN, and this isolation we are achieving, and these isolations are logical. So people have to carefully start looking into those definitions and see how those software is written, and we have to look at whether there are no vulnerabilities at that stage. So these are something very interesting, and from an academic point of view this is a brilliant attack, but from a commercial point of view it is really a big jolt to many. So with this what we have done in this IS4 course is to get you a big detail about we are trying to give you a holistic picture. Right. So what we will do in the IS5 course, that will be in December 2018 or January 2019, we will concentrate more on the hardware side, on the digital hardware and microarchitecture, and we will be talking about some of the recent hardware developments that have basically helped in trying to get out of many of these security issues. Hopefully we will have a much broader understanding of these type of architectural interventions to ensuring security, and we can give a very nice sum up. Finally, end up this course, please note that the hardware, the digital hardware as you see in the screen, is the foundation, and if the digital hardware is weak, whatever good things you do in the top can be leaked. So it is very important that the digital hardware and the micro programming level, the microarchitecture, has to be extremely strong and should have lot of security orientation into it. So when we design a microarchitecture, when we design a circuit, we should have a lot of security. The thought process of the designer should be more security oriented. What is that is something which we need to basically talk about, debate, and that will be part of our information security 5 course. I wish you all the best in this course, and I hope many of you will take the exam and get yourself certified. I also thank the Information Security Education Awareness Program of the Government of India through the Ministry of Information Technology for actually enabling us to make these course materials and giving us the platform where we can basically develop this material, and of course the MOOC platform of IIT Madras, which has enabled us to deliver this course and reach many of you. I am sure it is going to be a very, very important exercise for all of us to see that we have a very safe and secure digital world to live in. Thank you very much.